Hi.
It works the same.
Nice of you to come. We're missing a few. Do you think they've taken the test? I assume you've all taken the test? How did it go?
Your scope question.
My what question?
Multiple choice question on scope. That was.
Well, I bet you got the right answer.
I missed two, and it had to be.
I missed at least one.
You only missed two, that's pretty good.
Everybody. I think we all.
I think you're down and
Well, we'll have to see if it was the same questions. I'll be happy to do that. So, how's your semester going? 4 weeks away. Well, you know, we have a week off coming up. Let's see, today is the 7th, so 3 weeks, no, 2 weeks from today, 2 weeks from today. And after that, I think we only have 2 weeks left. So does that mean we have 4 weeks of class in front of us?
Three more days.
Okay. Well. Okay, well, let's keep going here. I'm going to go back and revisit just briefly something we talked about last time. We're talking about how to find things at runtime in different memory locations. And so, just to remind you, we looked at quicksort last time, and we noticed that split is nested inside of quicksort, but it is using a variable that is local to quicksort. And we talked last time about how it finds that variable at runtime. So I'm going to skip down to a picture here. These represent activation records, so quicksort is called, and then it calls split, which calls itself recursively. But there needs to be a way to get at pivot, which is in quicksort's activation record. And remember how we got that last time? What was it that we had to introduce into activation records to help us find it? But it's a thing in the activation record that does what? Where does it refer to? It points to the activation record of the caller, which is quicksort. We called it the nesting link, also called the static link. So that's what we call it, and we call that because it represents pointing to something that you're nested inside of. And so we add something new to the activation records. We add a nesting link. And the nesting link for all of these calls to split all refer to the same activation record of quicksort. So that's kind of where we ended last time. We went a little further than that. So what we want to talk about now, and again, we started to talk about it last time, was how do we make the decision? I mean, consider yourself as a compiler writer, and you want to generate code that will automatically reference non-local variables in nested functions, like pivot. Now, how are you going to do that? You need to know where it is relative to yourself on the stack. So if there's only one level of nesting, it's pretty easy. If you're inside of a function and you're calling something up, let's see, if you're calling a function at the top level, well, it's not considered to be nested inside of anything. So the proper thing to do for the compiler is to generate code that will set the nesting link of that outer function that you're calling to be No, because it's not nested inside of it. If you are calling something nested inside of you, you are the activation record that it needs to refer to. And so you set the nesting link to yourself. And you're calling from outer to inner. And if you're calling from inner to inner, you can really only see, that means you're in the same level. You can only see each other. But if you're siblings, defined in the same containing function, what's your nesting link? It's what? Yeah, you have the same nesting link, exactly. So if you're going to call a sibling function, then the code generated at runtime by the compiler writer needs to set the nesting link to be the same as your nesting link, because you're at the same level. Right? All right, so what I want to do is I want to look at this picture. Now, this is where we left off last time. And we need to apologize to, what is your name back there?
Josh
Josh.
Anderson.
Josh Anderson. I mean, of course, both F2 and F3 are visible here, and I'm going to show you code. I posted it because they're not really defined like this. They have to be defined serially, right? And so, in this particular case, if F4 is going to call F3, we better put F3 first, right? Except, what if I want to allow F2 and F3 to call each other? And so in that case, I do something like this. So this is going to be that picture, and I better draw the picture on the board. Of course, that requires having a pen, and naturally, there's no pen. I'll get one from the other class.
Beautiful. It's safe. Wow. It's all jump. Yeah, it's so there's like this huge rat's nest cable. It's just like all usually it's like the back of servers and stuff. There's also nothing here. Okay, I don't know what that is. Don't like that. It's cool. The cable guy? Cable guy? Oh, cable. Okay, got it. I'm sorry. Anyways, the markers are gorgeous.
So I'm going to do F3 first. So this is function F3. And I'm going to do function F2. Okay. We can certainly call F3 from F4. And if F0 is defined at the top level just like F1, well, then that can be seen too. And so we're going to use this, not only for this, but for an exercise where we actually decide how to set these things. But I thought I would write this, I didn't really have to do it this way. I could have just left this, well, I couldn't have actually, because the way I wrote it is I put code inside. I'm going to let F3 call F2. And F2, I'm redoing it so it takes a bool. If it's true, it's going to call F4. If it's false, it's not going to call anything, and it'll just print something. And the top level code down here just calls F1 with true. So this mirrors what we have here. F1 is at the top level. I don't have F0 here. And then inside of F1, we define F3 and F2, as you can see. So, but I'm using the and that allows me to define mutually recursive functions, if you will. Remember the and? We did it with is even and is odd and that kind of stuff and all that. So it allows you to define functions that can see each other. The way you have to do that in other languages is you have to have some kind of a forward declaration for the second one, so it can be called from the first one. Okay, in any case, F3 and F2 are defined at the same level. They're nested inside of F1, but F4 is nested inside of F2. And so now when I call F1 with a true, we come here to F1 and it says, let's call F2 and pass that true along. So we'll call F2 and the true branch is here. And so here it'll print out that we're here. And now we define this nested function, which we'll call F3. And so we go to F3, and it's going to call F2 with a false, which will come down here and do that. Now, I don't really have local variables, non-local variables that I'm accessing here. So this actually doesn't illustrate a whole heap of a lot. But it does show you how you can, in ML, define this nested structure. Now, can you all see this? Okay, good. So now, oh, I have it here too, how convenient. What I'd like to do now is I want to fill out this space called algorithm. In other words, how are we going to set the nested link? And so the first one says, I'm the caller, F1, and I'm gonna call F0. So F1 is gonna call F0. They're both defined in the same scope. You can assume that F0 is defined first if you want. Well, that's certainly doable. So I need to set the nesting link for F0 when I call it. This has to be done by the caller. What am I going to set it to?
F1's nesting.
Pardon me?
F1's nesting.
I'm going to set it to the same as F1's nesting link. That's correct. Which in this case, since they're top level functions, would be known. All right, now let's have F1 call F2. So it's calling down a level. So it's gonna set F2's nesting link to be itself, which is F1. Okay, now F1 is calling F3. Same thing, right? Because those are, F2 and F3 are at the same level. They're both nested. Okay. And so when we say itself, we're just gonna take the address of the activation record for F1 and stick that into the nesting link slot for F2 and F3. All right. Well, now let's have F2 call F1. So what's the nesting link? Say again.
Is it a caller?
No. The nesting link represents the context that the called function is nested within. What is F1 nested within? Nothing. That's right. So it's going to be null. But how does it know that?
said it's outer, activation, which would have been.
Yes. So the compiler says, the compiler keeps track of all of these levels during compile time. And so it says, well, F2 is defined at level 1, because F1's up in 0, right? So F2 is defined inside of F1, but F1 is at level 0. So you subtract 1 minus 0, and that says it needs to follow its nesting link one time up, and whatever the nesting link is there, that is going to be the nesting link of the call. Now, if you look inside the activation record for F1, it's going to have a null there. We already decided that, because it's not nested inside of anything. So when F2 calls F1, it's going to go to the current activation of F1, which is the one that's already been, that is currently live. How do we know that there is a live activation for F1 when F2 calls F1? Because F2 is nested inside of F1. The only way that it can be running is if F1 is running, right? Okay, so there already is an activation record for at least one call to F1, so that F2 can even be considered. And now F2 wants to call F1 kind of recursively, if you will. I mean, you know, F1's already running, it's going to make a recursive call for F1. So it goes up one link in the chain to see what's in that nesting link, and that's what gets copied to the new activation record for F1.
When you're calling back up the chain, like F2 to F1, are you making a brand new activation record?
Yes. Oh, every time you call a function, you get a new activation record. Oh, you have to.
Yeah.
Just like recursion. You know, I mean, you'll have different variables, like if you're passing stuff. Every time you call a function, you get a new activation. Unless it's tail recursive, and you're calling yourself.
Or a static method, right?
Well, yeah. Well, a static, no. Any function and method still, it's an activation record. Because static methods have local variables. Yeah, no, every function call has an activation period. So, we know that there already is an F1, otherwise F2 can't even be in the running. And so it will go up the difference between these levels to find what is the proper nesting link, and so it'll set it to null. All right, let's have F2 call F0. Now, again, it can't, it's not going to reach F0 itself. F2 isn't going to find F0's activation record, but it doesn't have to. How come? Because it's at the same level as F1. Therefore, if F0 and F1 are in the same level, they have the same nesting link. They've nested inside the same thing, which in this case is the top level. So it still does the same thing. It's going to take 1 minus 0 is the difference in the levels. It will just follow its nesting link in its record up 1, which to find F1. And whatever that nesting link is, it's going to stick that into the activation for F0 when it executes. So you see why this is static link. It all has to do with the code itself, the layout of the code. Okay, let's have F2 call F3. You may have to look over here now. F2 wants to call F3. They're at the same level. 1 minus 1 is 0. So it's going to jump 0 from its own activation, which means it's not going to move anywhere. And it's going to take whatever its nesting link is and put it into the activation for the function it's calling. Because obviously they have to be at the same level, so therefore they're both nested inside of F1, and that's how it gets the most recent activation record for F1, because F2 has it inside of it when F1 called it. And so F3 needs the same activation record. So it's going to be itself, which in this case, well, not itself, it's going to be, same as F2, right? Okay, now let's have F2 call F4. Question, Brian?
Can you re-clarify what itself means then?
Itself means it's its own function. It's its own activation record. Let me write that. That's a good idea. Let's rewrite that. Its own activation record. So whatever the current stack pointer is. Yeah, why don't I say that? Current stack pointer. So we should say that in each case. Great. All right, so now what am I gonna do then when F2 calls F4? Its own activation record, because it's calling one level deep. And you can't call 2 levels deep because you can't see it, right? Because that would be, that would be in a block that you can't see. And so let me push this down here, but in this case, that's F2. All right, very good. Now, let's have F4 call F1. So F4 is at level 2, F1 is at level 0. So how are we going to find the nesting link to give F0? We're going to go up 2. 2 minus 0 is 2. So what we're going to do is we're going to follow our nesting link for F4, which points to the activation record for F2 that's currently running. And then we'll follow its nesting link one more time to find F0. And whatever nesting link is in there, that's what we have to give the new call to F1. Well, it's going to be in home. But it's 2 jumps on the chain of nesting links. Okay, how about F4 calling F2? I mean, whose activation record is it? It's going to be the nesting link for the new F2 call. F4 is calling F2, so we need to give F2 the proper nesting link. And which activation record is the proper nesting link for F2? F what?
F1?
F1. Now how's it going to find it? Well, F4 is 1 level down from F2, 2 minus 1 is 1. So it's going to jump 1 level on the chain of nesting link. In other words, it's going to follow its nesting link 1 time, which will point to the most recent activation record of F2, and then it'll look inside of there and see what's in there. What would be the most recent activation of F1? Is F2's nesting link, right? That's what it'll put in the new activation for F2. You getting it? Yes.
The levels are determined at compile time.
Yes.
On code inspection based on blocks.
Yes, exactly. Exactly. Yeah. That's why they call them static links. These levels are because of your code that you write. Okay. So F4 is calling F2. F2 needs to have its nesting link set because it might need something from F1. Accessing a non-local variable that's in F1, right? Well, so F4 is going to jump back 1, because 2 minus 1 is 1, to F2's activation record, and take that nesting link and put that into the new activation for F2. Okay, now let's have F4 call F3. It's going to be the same thing. 2 minus 1 is 1, so it's gonna take the nesting link from F2 and stick it into the new call to F3, because they're at the same level, they have the same containing function. And so the most recent activation of F1 is going to be what is needed as the nesting link in F3. So it's going to be F1 again. All right, so in general, what do we do when a function calls another function and they're defined at the same level? We just copy our nesting link over, because if we're at the same level, we're nested inside the same thing, right? So we copy ours to the call function, copy our nesting link. All right. Now let's suppose I'm at a deeper level calling up.
You do 2 minus
So
1.
my level is deeper from the caller, and I'm calling up to something. How am I going to find the nesting link for that call function?
N minus 1,
I'm going to go n minus 1, right, so I'm going to follow
or N minus N.
n minus n nesting links to find the nesting link. And so let's be clear about that. N minus 1 times, I'm going to go up to some activation record, and then I'm going to look in that and say that whatever nesting link is there, that's the one to put into the one I'm calling. And now, if I'm calling something deeper than myself, I can only go one level because you can't see anything nested inside of you another level. And so you just set it to your own activation record. You are the activation record. So here I should say copy our nesting link. And here we should say copy the stack pointer, our activation record, to the call ease activation record. All right, so the stack pointer is always pointing to the currently running function. And so whenever we're calling something one level down below us, we just copy the stack pointer. If we're calling up, we follow the chain and we extract the nesting link that's there. And if we're calling at the same level, we just copy our nesting link. So, how you doing? Yeah?
I have another question. So I imagine that the nesting links are probably restrained due to scope. So if F0 had a nested function F5, would F4 be able to get at it?
No.
So
Yeah,
you could never-
just like if F4 had an F5, F2 can't get at it,
Okay, yeah.
because it's hidden inside that scope. You can only see at your same level or up.
So when the compiler is determining.
You can't go up and down.
Okay, so when the compiler is determining these levels, F5 nested in F0 would still have the same level as F3, but
We can't call it.
we can't call it
Yeah,
because of the scope.
yeah, yeah.
But
So we
the
don't break
level-
scope.
The level is abstract from the scope.
Yes. Well, yeah, well, scopes are nested within each other. So, I mean, they're related.
Is this gonna be available on Canvas? Like, fill that one, or do you have it like linked up there?
I wonder if it's up there. It might be up there in the files folder. If it's not, yeah, I can, it's not?
I just think it'd be very helpful.
Yeah, oh no, I'll do that, yeah.
It just doesn't take us back too far. Can you repeat like what the purpose of an inline function is?
Of a what?
Inline function?
What's an in-
nested function?
Oh, a nested function.
Yeah, sorry.
Okay, that's not an inline function. The purpose of a nested function?
Yeah.
It's, well, who wants to answer that, or?
It's
Go
recurring.
ahead.
You contain the function scope to your other functions, so that way you don't, or it can't be called anywhere else.
Yeah, so we're limiting the scope. You always want to give something the minimum amount of scope it needs. So that's why quicksort defines split inside itself. Yeah. So that's why we have nested functions. And you may not be used to them, but in a limited sense, you get these with inner classes. Because whenever you instantiate a new object, instance of an inner class, and you call a method on it, it can access the containing object, right? Well, this is doing the same thing with functions, and so activation records are the containing thing where we find the variables. Yeah,
So these are all sitting on the stack, right?
this is all in the stack.
How big is like an activation record?
Not
I mean,
very big.
They gotta change like how many variables you pass and stuff, right?
Oh, sure, so, but
How-
in most languages, the activation record is of a fixed size, although I showed you an example of that is a bit different. Keep going.
Well, I'm just wondering, like recursively, it seems like you get really big.
Yeah, it depends how big your stack frame is, your activation record is,
So,
but that's why
like-
we need big stacks.
Are we talking bytes? Like a byte?
Well, yeah, but typically they do, the stack operates in words,
Right.
ints, right? And they can pack things in, you know, if they need to, and so that'd be fine. But yeah, I mean, if you take two parameters and you've got two local variables and they're all ints, then 4 times the size of an int, plus the extra stuff that we need, all the links, are in the stack. We have no choice, that's the only way these things work.
And that's where the stack overflow exception comes from, when you get
Mhm.
a recursive call that never ends.
Exactly.
The fact that you exhaust your memory with stack frames.
And so your stack pointer tries to go out of the allocated memory, and the operating system will catch that. It's just that the default stack size for most development environments is pretty big, you know. It's like, well, what is it? It's at least 4 meg, but it depends on your compiler. You know, how big they decide to make the stack. And you have control over it, right?
Right.
Yeah, you can, with the compiler option, say, make the stack this big. No, you're totally right.
Well, I'm just.
You can consume a stack in a hurry if you're not careful.
Right.
Yeah. So recursion is a big problem with that. Now, and so that's another reason to do tail recursive functions, so that it doesn't. A tail recursive call always reuses the same activation record for every call of that function, because it doesn't need to keep any of the other stuff around. Yeah,
The set nesting link document is on pages.
in the files folder?
It's called the unfiled.
Oh, so it's in the unfiled folder. It's called set nesting link .doc or .x or something. Thank you, yeah. I assumed it was up there, but I didn't remember. Yeah, very good. Yeah, so it would be a good exercise, you know, to go through a blank one on this and see how you do. Let me make sure I did it right. We should have null, F1, null, F1, which is the same as F2's link. Yeah, no, I should have said F1, which is the same as F2's. And then, where are we now? We're on F2 calling F4, and that should be F2 setting to self, yeah. And then here we have null, because we're calling F1. Here we should have F1, because it looks up one level, likewise here. And then here it's the same as my link. Here it's look n minus levels back, and here it's set to the stack pointer, my own self, my own activation. That's good. Okay, well, guess what? We're not done with this, but we're having fun, and that's the most important thing. But the plot thickens when functions are passed around as parameters.
You're exactly right.
So when a function gets passed as a parameter to another function, and then that function gets called inside of the other function, it may have to access something that was non-local over in its environment, in its definition environment. So what really needs to get passed? Well, why don't we just pass a nesting link? Yeah. So again, these nesting links are very important. So here we have, and we've seen this kind of stuff before, but this is a little different. So add X to all takes X and a list. And what we're going to do here is we're going to take advantage of map. Map will call a function on everything in the list. We'll just return that. Well, what we want to do, well, this is like your homework, Inc. all for chapter 11. We want to add X to whatever's in the list. So Y represents whatever's in the list when map executes this function on the list. And what's going to be added is whatever X was when we called add X to all. The thing is that we're passing add X to map. So now we have to say, how is add X going to find X when it's been passed over to map? Well, the only way it's going to find it is if it can refer to the activation record of add X to all. So what really happens is that a nesting link gets passed along with the function. So that last bullet, to make this work, the parameter add X passed to map must include the nesting link. And this is what we call a closure or a delegate. So this motivates the issue. So what's going to happen is when we call map, map is passed this thing called add X, but we can't just pass the code for add X because we have to have a way of accessing X. So here's the nesting link that points to the activation record for add X to all. This is when we're about to call map. This is what we're going to pass to map. So that's what we call a closure or a delegate. Now in object-oriented languages like C#, instead of a nesting link, we're going to have a reference to some object. And then the object, of course, can access anything it needs from its class. But with nested functions, the surrounding context is the containing function. So when we pass add X to map, not only does the code for add X get sent, but so does this nesting link. And so a closure is what is passed. So a closure is created, and then an address to that. And you might ask, where does the closure go? Well, the answer is different under different circumstances. And we'll talk about that. But for now, just understand, and I know we've already talked about this, just understand that when we pass a function as a parameter, we also have to pass its referencing environment so it can find the non-local variable sequence. Now, it's not just when we pass them as parameters, but as you know, functions can be returned as values from other functions, and we can compile them or create them on the fly with anonymous lambda expressions. So, and you saw us do this in D, right and left, you know, we did it all kinds of times in D. We would return a delegate, and that delegate accesses something that's not local to the delegate. It's in its enclosing environment. Well, then that's why the delegate is a delegate. It has a pointer to the activation record. And then the last thing we want to say is some activation records have to stick around longer than you might think. They have to stick around after they finish executing. And that's when we actually return something. So let's take a look at this. let's look at fun to add x. It's a lot like it was before. The only difference is I'm returning this function. But this function needs to access x. But when I return it, fun to add x is popped off the stack and it's gone. But I still need to hold on to that x somehow. So let's look at the calling situation here. And we've done this over and over again. I'm going to create a function by calling fun to add x with a 3, and it's going to return me this function, which adds 3 to its argument. So now when I pass a 5, I'll get an 8. But how does it access the 3 that was sent and bound to x when fun to add x is gone? It's finished executing. And again, the answer is, well, we're going to have to somehow have a closure to that. And so here's the point where we have called fun to add x here. So this is fun to add x. Here's the main little test code. And what's going to happen is add x, of course, has this closure. This is going to be its code, but it also needs to reference the activation record in which it was nested, where x was defined. Now, when we return from here back to main, when we're about to call f with a 5, I still need x. And so this activation record really can't disappear totally. Question is, where is it going to be? And in D, it's moved to the heap. How ML does it, I'm not sure. It could do the same thing. It could put it on the heap and then it gets garbage on. The point is that activation records need to persist beyond their execution when their environment is still needed. And this happens when you return a function from a function. It's still a nested function from a function. It still needs to access what was in the containing function. Is this making sense? It should be. Okay. All right, so that's the story. You know, the problem is the activation is finished, and the solution is, of course, to hold on to it, and that leads to garbage collection. So we're going to talk about that. However, let's summarize what we've talked about. A function closure is basically a pair. It's a nested function, so it, we're going to point to some code that was defined inside of another function. But it also has this pointer, if you will, to a region of memory that has the non-local bindings that it needed, like X, that were in its lexical environment. So it could be that that activation record has been moved to the heap so it can still be accessed. Now, another way to do that, and I've got a slide coming up, we're going to actually talk about this. Another way to do that, instead of always having the activation record stick around, and this is a lot of overhead, but Python does it, and that is every time you call a function, you pass a hidden dictionary, a map, that has all of the things you'll need that came from the calling environment. And it just references them right there without having to follow links, but it uses more memory. All right, hence we have what we call delegates or closure. All right, well, let's conclude, just wrap up chapter 12 with the basic things we've discussed. We talked about activation records. They hold the local variables in a function. They go on the stack, except old languages didn't even use a stack. They just had one statically allocated activation record for every function. It's faster, but you can't have recursion. And so, kind of a pain. So using a stack works out nicely for languages that allow recursion. However, when you allow nested functions, you have to be able to access the nesting environment that you were defining. And that's done by holding on to a nesting link pointing to the activation record for the continued function. but they cannot always be deallocated on the return of the function. They may have to stick around because you're returning the next function from the container function. So there we have chapter 12, and we're done. How you doing? Anybody take the test today? How's your brain? You doing all right? Okay. Well, let's talk about garbage collection, but before we talk about garbage collection, we've got to talk about the heat, because that's where it takes place. So let's do that. So we're going to talk about dynamic memory allocation, and I know you're familiar with that. And if you've taken 3370, you're really familiar with that. Who's had 3370? Am I correct in making that assumption that really gave you a deeper understanding of it's one of the reasons for the course. So, you know, in a language like C, you could use malloc, or in C++, you can use new for anything, and then you can use new in, of course, Java and C# for objects as well. And so, you know, there's a lot of memory changing at runtime. And of course, there's activation records on the stack, and a lot of stuff goes on the heap, whether you explicitly do it with new, or whether it just happens because you're using a class that uses the heap, like strings and stuff like that. So because of that, there is this thing that gets stuffed into your executable if you are using C, C++, or D. It's the runtime memory management code. If you're using Java or C#, then the virtual machine or the runtime has all of that logic to take care of managing the memory. So, we've already talked about stacks. We'll just say a quick word about it. Let's see, Jared, that's your name, Christensen? All right. You're the one that asked, doesn't this take up a lot of space? Well, let's take a look at a way of doing stacks.
Really, you can act like you don't know my name. Not very name.
I knew your name, but the only reason that I said what I did is because you didn't look at me as soon as I said Jared. You just kept looking ahead. So I thought, I'm getting old, maybe I forgot. Even though you've had like 4 or 5 classes from me.
You may not have changed.
Well, you don't hold the record. There have been students that have had 8 classes, but that's hard to do. 'Cause I haven't taught some of those for a long time. That means they must have been here for a long time. And it's true. Okay. All right, well, let's just talk about how to do a strategy to implement activation records on a stack. So let's suppose we have, you know, here's our stack pointer. We're going to grow down, okay? So our stack pointer is pointing, you know, somewhere, and this is an unused portion of the stack. Well, now let's just suppose we call a function, and now we need to push an activation record on the stack. Well, a typical way to do it is like this. What was the stack pointer gets stored here so I can restore it later. In other words, the stack was pointing at some other activation record. And so now it's going to point to the activation record we just pushed. But here's the dynamic link to restore the previous one, which was up there in slot 8. And then everything that needs to be there is there. Now, of course, there's only 3 things here, so that's a boring function. But the code generated by the compiler will call a push on the runtime stack that says, I need this much space. However, it will actually give a little extra because it needs a place for the dynamic link. But everything else has to be here, the return address, any local variables, whatever else. But this is a very typical way of doing it, is the dynamic link goes on the bottom. And so the stack pointer is pointing at this location, which means it's going to use whatever it needs by stack offsets to get the local variables while the function is running. And then when the function exits, the stack pointer is set back to 8 where it was when it's popped. So it's a pretty simple way to do it. You just push stuff on the stack and the dynamic link is what the stack pointer was before you got called. So let's suppose that we have to call another function from this point. And let's suppose it doesn't use much, and just for grins, we're gonna say it only needs 2, which means it really needs 3, so it's gonna use these 3 right here. And what gets put here is what the stack pointer was. So when this thing is finished, it can restore the stack pointer back to the previous activation. Now, at this point, there's nothing else we can do. I mean, we can't even do a push 1 because we always need 1 extra for the dynamic link. So anyway, that's just a scheme, and it's a traditional scheme. There are certainly, optimizations that can be done, but it's that simple. So implementing the stack is not a big deal. Now let's talk about heaps. Now this is very different. It does not have a last in, first out, or any kind of ordered way of managing. It's being managed. It's totally up to you when things get deallocated when you call delete. Of course, you don't call delete in some of the languages you use. So we're going to consider a language that does call delete, like C++ or Pascal or even D. So here's one of the strategies for using the heap. This is just a bunch of memory. One strategy is called first fit. In other words, we have this big section of memory called the heap in the beginning that's all unused, and there's a pointer at the beginning of it. So somebody asked for memory, good. We'll allocate some memory for you, and now the heap pointer is going to point right after that allocated block. And you want some more? Good. We'll give you some more. Now the free pointer is going to point to after that. Now let's suppose you now delete the first one. Well, if you delete the first one but leave the second one intact, because you're finished with the first one, then we're going to have the free pointer point there, but inside here we're going to have to point to the free block after the second one. And so it can be a little confusing. But again, if you've taken 3370, you saw how to do that on the class level. So here's the idea. Imagine that this is the heap memory, and we're going to grow up here. Typically in real programs, the stack grows down and the heap grows up, and when they meet, you bomb. So, all right, so there's always a variable, and it's probably in a register, just like the stack pointer, that says this is the beginning of the free store, the heap, and this is how much I have in the heap. Now, for this example, it's pretty small because it fits on the stack. This says this whole thing is 10 bytes. And the thing that is always after this is pointing to the next one. Well, there isn't a next one, it's all free, and so we'll have a negative one. That's not a valid memory. And all of these will be offsets anyway. But for now, we'll just say it starts at 0. All right, well now let's suppose, all right, so this is what we have. We always have, this is how much is available in the block above me. And this is going to be the block after me that is available. So it's kind of an implicit linked list. But of course, there's nothing there in the beginning. So now let's suppose we make an allocation. So here we're going to say, oh, I need 4 words. Well, then I'll get my 4 words, but there'll always be this little bit of overhead. Because this is going to tell me now where is the, let's see, that's the size. That's the size. So it's 5 bytes total. And this is how, when we delete something, it knows how many words to free up. So this is, so now that we've done this, we've just allocated 5 words on the heap. Now the start of our free store has been moved up to the next one that's free. All right, now let's do something after that. So now, after having asked for 4, let's get 2 more on the heap. We'll first fit, we'll just say, we'll just do the next stuff, whatever's there. So, we'll do that. Now, I asked for 2, but of course, I have this overhead of saying how much is here altogether, which is 3. And then the free, since 3 was being used, and the free pointer was 5, 5 plus 3 is 8. All right, well, that's the situation. Now, you've got the pointers for these. You've got a pointer to here, which is the beginning of the memory available here for that first allocation. And you've got a pointer to here, which is the beginning of that memory from the second allocation. Now let's do a delete. So let's deallocate the first one. Well, that means that I'm going to take what was this first block. Now, when we say P1, P1 holds the address to this memory. We always back up one and to find the information of how big the allocation was. You get this pointer because that's the usable memory. You don't, and then we just back up one and we see, oh, it was 5. So I'm going to make these 5 things free now. And what was the free pointer is going to go here. So I'm basically implementing a stack with an implicit linked list in this linear memory. So now if I get another request, it's going to try to fit it here. And then it'll know that the next free block starts up at 8, where it was before. So let's do one more request. Now we're just going to say, well, allocate 1 for me. So before I even give you 2, this, what's going to happen? I'm going to say, I need a size 1 on the heap for my use. And what's going to happen? So how many am I going to allocate altogether? 2. And they're going to go here where it was free. Okay. And so this will be the one that I can use. This is where I will have the size of it. And the size is going to be 2 because it's the size of the whole block. That's how the heap manager knows how to move things around. And then, what is free start going to point to? 8. So it just grabs it from here, right? And it returns this address to the caller. There we go. Oh, wait a minute. Oh, no. Let's see, why did it do that? Oh, because it had enough space left over. Okay, that's true. Oh, yeah, that's right. Let's go back to here. 8 was the next one after here, right? 8 was the next one after here that was free. So what I'm going to do is I'm going to use up these 2, but I still have this free, no sense in throwing it away. What I'll do is I'll say, okay, this is the next one, but I'm going to put an 8 in here and make it the next after that. So first fit actually will use whatever's left over. So that's what we do.
So,
Okay.
if there weren't 2 empty blocks there, would it then just throw away the space because it can't fit? So there's 1 empty
What
block.
first fit does is it'll follow the link chain until it finds one big enough. And if it doesn't, then you'll get an error. Right. So we have a problem here, memory fragmentation, right? That can happen. It is a problem. And we're going to talk about that and what we can do about it. Right, but that's the whole purpose of having a linked list, is that I'll search for one, and then I'll just have to, align up the arrows again, according to the information that's there. And that's why, this number always tells me how many are free contiguously in that block. So we get all these blocks, and there's all this implicit linking that's going on in a stack. Now, the order that we do things makes a big difference. I know we don't have the picture right now, but it turns out that this one, even though there's enough memory there, it's too fragmented. Here I'm gonna ask for 4 and then 4 more. Well, that uses up the whole thing. Because 4 plus 1 is 5, 2 times 5 is 10, because of the overhead. And so it's totally, I can't do it. Now, I can deallocate both of these, but when I deallocate both of these, they're pointing to each other, and they're both size 5. Make sense? Because the algorithm does that. They were divided into 2 and I used them, and so when I deallocate one, say this one, then the free pointer is going to point here, and when I allocate the second one, that's going to be the head of the implicit stack, and it's going to point back to here. And so they both will say size 5. And here I ask for 7, and I've got 10 free bytes, or 10 free words on the stack, but they're segmented. I got a problem. So even they're contiguous in memory. But because of those arrows that are going on, and the way I was used, it's not considered all contiguous. And so the idea there is we have to do what we call coalescing. We need to have a smarter deallocate method. And unfortunately, this is a lot of overhead. But somehow, we need to be able to determine if I have 2 adjacent blocks in memory, why don't I just combine them into one bigger block? And that's called coalescing. Well, how can we do that? Well, one way to do that is that we actually have a separate list that is kept with the beginning of all the blocks, and they're sorted in address order. And then we can go through all of the blocks, check their size, and see if their size makes them bump up against an adjacent free block. And if it does, we coalesce them and change to the size to be the sum of the 2. But that's a lot of extra work, right? Well, these are things that have to be kept in mind with any project. It's just the way it is. Okay, we've already talked about fragmentation, so let's look at, and this will be the last slide. So let's just look at what happens with this. Then we're making some changes here. So first I'm going to ask for 4, and so I'm going to get these 5, so I can have these 4. This points to that's the size. This points to the next free block. Okay, and then I'm going to allocate 1, and that's going to do this. So these are all being used, but now I'm going to deallocate this one. And so when I deallocate this one, this becomes the new head of the list. And I put in here what was the pointer to the beginning of the free list. And so my memory is fragmented with the first 3 calls there. And so this one will fail. So, and there's no coalescing that can be done here, right? I don't have 2 adjacent free blocks that can be made one free block. So I get fragmentation. What do you do? We'll talk about it next time. Let's see.